4, we're going to be talking about the normal distribution and a lot of objectives. So we'll probably split this up into 2 different videos. Here we go. All right, so let's talk about what normal distribution is. Another way, a name for it is called the bell curve or the Gaussian distribution. A lot of people call it the bell curve because it looks a bit like a bell. So if you kind of follow this up and down, to a lot of people that looks like a bell. So it is bell-shaped, symmetric about a vertical line through the center. So here is my center, and it's the same on this side as it is on this side. Mean, median, and mode are all equal and located in the middle. Okay, that's important. So they have different pictures, and basically what they're doing is increasing the sample size. So this is a sample of 100 men, and notice it's kind of bell-shaped, but this side is not the same as this side. Notice this one is here and this one is up here. But the increasing the sample size is the same test, or the same experiment, but it's survey, but it's increasing the sample size. It's still not identical left to right, but notice as we increase the sample size, it looks more and more equal on the left side and the right side. Okay, so this is still considered a normal distribution, even though it doesn't really look 100% identical left and right. We just need to increase the sample size. All right. Let's see, hold on. There we go. The shape of the normal distribution depends on the mean and the standard deviation. So these 3 graphs have the exact same mean, but the standard deviation is different. So we've got this one, which is really flat. This one is going up like this, and then this one is way up here, right here. That all of it depends on the standard deviation. As the standard deviation increases, the distribution becomes more spread out. So this one right here, that one has a smaller standard deviation than this one right here. So this one has a bigger standard deviation than this one. Okay, this is called the 68, 95, 99.7 rule. And it has to do with the percentage of items between a standard deviation away from the mean. Okay, so let's suppose we have a mean of 0. Oops, sorry about that. We've got a mean of 0, and let's suppose we have a standard deviation of 1, just to make it easy. So this would be 1 standard deviation above the mean, and -1 would be 1 standard deviation below the mean. So if we look at all of our data items, 68% of them will be between -1 and 1. Again, assuming our standard deviation is 1. This technically is the number of standard deviations. So if our standard deviation is, say, for example, 10, let's see if I can clear it. There we go. So let's suppose our standard deviation is 10. Then 1 standard deviation above the mean would be 10, and one standard deviation below the mean would be negative 10 and 20 and negative 20. If we had a standard deviation of 5, then one standard deviation above the mean would be 5, and here we have negative 5. Again, assuming our mean is 0. I hope that clarified something to somebody. But anyway, so this rule says that approximately 68% of all data items are going to fall within one standard deviation of the mean in both directions, right? In both directions. So above and below, that gets 75% of all the data items, okay? If we go 2 standard deviations, so 2 standard deviations below, 2 standard deviations above, this now will cover 95% of all data items will fall within 2 standard deviations, both above and below. And then once we go to 3 standard deviations, now we're at 99.7% of all data items in a normal distribution will fall within that range. Okay, so basically we got almost everybody here. Basically what this is saying is that you are a pretty rare item if you are more than 3 standard deviations away from the mean. It just doesn't happen very much. 0.3% would fall outside of 3 standard deviations. Okay. All right, so let's kind of clean that up a little bit. And all right. Male adult heights in North America are approximately normally distributed with a mean of 70 and a standard deviation of 4. Okay. Find the height that is 2 standard deviations above the mean. Okay, so I have a mean that equals 70. Okay, and a standard deviation that is equal to 4, and I want to be above the mean. Okay, so a height that would be 1 standard deviation above the mean, I would add 1 standard deviation to the mean, and this would be a height that is 1 standard deviation above the mean. It's not asking for 1, it's asking for 2. So I'm going to take and add 2 standard deviations to the mean, and 78 inches would be the height that is 2 standard deviations above the mean. If they had asked below, if they had asked instead of above, they had asked below, then you would subtract. So you would take your mean and you would subtract 4 inches. Okay, so 66 inches would be 1 standard deviation below the mean. And if we subtract 2 standard deviations, now we're at 62 inches. So this height would be within 2 standard deviations, but this time we're below the mean. All right. So 78 inches. Interestingly, they want to know what percent will fall between 66 and 74, keeping in mind the mean is 70 and the standard deviation is 4. We know it's 4 because we went from 70 to 74. So this is always going to be 1 standard deviation above, and this will always be 1 standard deviation below. All right, so we need to be between 66 and 74. So here's my 66 and here's my 74. And I'm going to count. This is 1 standard deviation and this is 1 standard deviation. We don't add them together. Okay, we count 1 above, 1 below. This is equal to within 1 standard deviation, which is this, and 68%. Okay, Let's see. Yep, 68% right there. All right. As you know, um, everything that we talk about has a different mean, it has a different standard deviation. So to be able to kind of compare things, what we do is we kind of, we compute the z-score. And the z-score really helps us basically compare apples with oranges is kind of the purpose of it. What it is, it the actual number that we get, oops, sorry again. The actual number that we get is going to be the number of standard deviations either above or below the mean. So if it is a positive z-score, then we are going to be above the mean. And if it's a negative z-score, we are going to be below the mean. And if we check the z-score for the mean itself, it will be 0. Okay, so the formula for that, we take the data item, we subtract the mean, and divide by the standard deviation. Okay, data item minus the mean divided by the standard deviation. And again, what that does is it kind of makes everything kind of the same so that we can compare it. Okay. All right. So the mean weight of a newborn infant is 7 pounds and the standard deviation is 0.8. Okay. Mean is 7, standard deviation is 0.8. The weights of newborn infants are normally distributed, and we want to find the z-score for a baby that weighs 9 pounds. So one standard deviation, we would be at 7.8. Another standard deviation, we're about 8.6. Another standard deviation, we're at 9.4. So you know this 9 pounds is somewhere in between 2 and 3 standard deviations. We're above the mean. What we're going to do is figure out exactly how many standard deviations it is above the mean. Okay, so we're going to use the formula. We're going to take the data item, which is 9 pounds, and we are going to subtract the mean, which is 7, and we are going to divide by the standard deviation, which is 0.8. So 2 divided by 0.8, we would put that into our calculator, and it should be 2.5. So this tells us that a baby who is born who weighs 9 pounds, their weight is 2.5 standard deviations above the mean. Basically, that tells us that they're a pretty big baby. And yeah, 2.5. Okay, so I want to talk about how we can use the z-scores. Okay, so let's suppose we look at, let's go back, sorry. What a z-score does is it tells us, or a z-score table tells us what percentage of data items are below that data item. So for example, we had a 9-pound baby and we had a z-score of 2.50. So 2.50. So this is, they would write it like this, 0, 1, 0, 2. So we would read this as, so this is my 1.4 row, and if I needed 1.43, 1.43, I would look at this number right here. our z-score was 2.50. So here's my 2.5 and here's my 0. So that right there, what a z-score table tells us is that 99%, approximately, a little over 99% of all babies have a birth weight of less than 9 pounds. Okay, remember it's always less than, it's always lower. Okay, so 99% of all babies born weigh less than 9 pounds. Actually, it's 99.38%. But yeah. Okay, so IQ. Actually, I think I'm going to do the IQ on the next video. Oh, nope, I am going to do it on this video, sorry. IQ, Stanford Binet intelligence test, normally distributed with a mean of 100, standard deviation of 16. What is the IQ score corresponding to a z-score of negative 1.5? So we know the z-score, we're trying to find the data item. So we have our z-score, negative 1.5, and we don't know what the data item is. We're going to subtract the mean, and we're going to divide by the standard deviation. Okay, the way we solve this, because it's an equation, we have to solve it, we need to multiply by 16, multiply both sides by 16. And multiplying by 16 allows us to cancel that 16 with that 16. Okay, so I am going to, grab my calculator and multiply negative 1.5 times 16, and I get negative 24 is equal to x minus 100. I have to take this 100, move it to the other side. I got to get x by itself. The opposite of subtract is add. So we're going to add 100, and we get 76. So an IQ score, or IQ, an IQ of 76 would be a z-score of negative 1.5. And we can, this is an I, kind of doesn't look like an I. Okay, we can look at what percentage of people, I don't know if I did negatives or not. Never mind. I don't have a table for negatives. Normally what you do when you have a z-score table is you actually have the positive z-scores and you also have negative z-scores, but I did not put it in the slides, so never mind. All right. This one actually is going to go on the next video. So I am going to